Good morning everyone, I am Mr. Ish. I wanted to challenge myself or task myself with this concept here, the continuity. I want to present this concept of continuity in a very brief but well explained manner, and so I'm going to attempt to do that in this video. Continuity with regards to a function is a curve which is relatively smooth or gradual in terms of its change, and it lacks the abrupt character or any interruption within that curve over an interval. But what exactly is continuity? Keep in mind the following truth, that if a function has a derivative at point A, you know it's continuous at that point A. But just because a function is continuous at point A, it does not necessarily mean you could calculate a derivative at that point or a good limit at that point. Anyhow, continuity is very well explained using this following definition. Limit as x approaches a value A, f of x is actually equal to f of A. What does this mean? It means that if supposedly you were to plug the value of x being A into your function, the value you would get in terms of your range, because here you're doing a domain and input, the output you would get would be exactly that value you would expect to get if you could literally put this value A into your function, and it would be a valid value on your curve. Very quickly, if supposedly this right here is my A value right here and this right here is a function, I've drawn an open point over here to show you that for whatever reason this function, which is just f or f of x, this value of A, when you plug into this function here, it does not generate a value because A doesn't exist on this curve. But for this definition to have been true, you need to have this as a closed value. You need to have been able to determine a good limit at this value, and you need to be able to show f of x is equal to f of A as x approaches A. There are basically three aspects that you need to understand for this continuity in a nutshell, one of which is this: the value A must actually be defined. You should be able to define it with regards to your function, because this value A actually happens to be within the domain of acceptable values for that function. What does that mean? It means you don't want to have a situation where A is not actually within the domain of that function because of some sort of presence of a vertical asymptote. Consider this right here. If A generates a vertical asymptote, you have a function which looks something like this. Like here's my f of x function. As x values approach A from the left or to the right, you end up exceeding out of bounds. This function exceeds out of bounds towards the direction of positive infinity. You couldn't literally put A over here for whatever reason, but you just couldn't do it. And here you know A is not within the domain of your function. A would not be defined. This would be a situation where your domain would be something like minus A going up to A, and then A going up to positive infinity. But here these values of A's are not literally included or part of your domain. So A must literally be defined, and it must be within the domain for this definition of continuity to work. This is just but one of the three conditions that have to be met. The next condition that you need to meet for this ultimate definition to be met is this: that the left hand limit of this function as x approaches A and the right hand limit must be good. And you cannot have limit values which are approaching positive or minus infinity, because technically positive and minus infinity, a function approaching positive or minus infinity as x approaches A is not technically a good limit value, because it's more of a theoretical or conceptual answer. You're really having a situation where limit did not exist, but you didn't want to say it did not exist. Rather, you said it in a more pleasant manner, saying that the function exceeded out of bounds and went towards positive or minus infinity. For the second condition to meet, left hand, right hand limits must be good, and they must be a good acceptable value, like a good normal numerical value. Let's show you graphically what that means, or how it would look like. If you have a function which looks something like this, here's A as x approaches A from the left and x values approach A from the right. Both of these limits are good. You would look up into your function and you would look across. You would actually have a good legitimate y value which would represent the limit, and this y value is not some sort of a positive or minus infinity. And then here you satisfy this condition number 2, and you're showing that you are establishing the concept of continuity. Situations where such right hand and left hand limits would not exist or be good, or would be something like this: a hyperbola as x approaches 0 from the left, as x approaches 0 from the right, what happens in one instance from the right, you're exceeding towards positive infinity. As you're approaching values, x values from the left, you're approaching minus infinity. Here, right hand and left hand limits are not the same, but let alone you're getting positive minus infinity, which are not generally acceptable answers. As another instance right over here, as x approaches any value, let's just say we'll call this a, right at this value, x value of a, you have one function which looks something like this, and you have another side which looks something like this. In this instance, as x approaches a from the left, you're coming at this value which would be, let's just call it minus y, and then as x approaches a value from the right, which is looking here on the top, you're looking at positive y. Here in these instances you have minus y and positive y. They're not minus and positive infinity, they're legitimate answers, but the left hand and the right hand limits are not the same, so therefore you don't meet this condition. To establish continuity, you have to show that the a value was within the domain and it was defined, and secondly, you have to have left hand right hand limits which are good, they're acceptable, and you're not looking at answers such as these. For the third condition to have met this definition of continuity, it is exactly this: f of x must equal f of a. The output you receive from here, we'll call that a y value. The output you receive here from this y value, they must literally be the same. The value you've plugged in terms of x must equal a certain value, and f of a gives you that certain value, and they're both the same. How can we show you this graphically? And if supposedly this seems like you're trying to say too much when you're not really saying anything, that's not the case, because look at this situation right over here. We have a value over here, and we have an open value right here, and what we have over here is this. If we were to read across over here, we will call this, let's just say 0, 2. If we were to read this across, we would say this is 0, 6. In this instance, if you look at f of x, if you literally look at f of x, and you look right in on your curve, f of x here, in terms of limit as x approaches a, just looking at f of x, you're getting a limit value of 6. But when you look at f of a, and a is very well defined here, because when you do f of a, you actually get a value, but that value happens to be 2. Here you're getting a 2, here you're getting a 6, and they just don't equal to each other. You don't have this f of x is equal to f of a. In this specific diagram, you can clearly validate the first two conditions, that an f of a value exists, that f of a over here is defined. You can clearly establish that. You can also clearly establish the second condition: the right hand and the left hand limits are good. Here's my right hand limit, here's my left hand limit, they're good, and they're giving you a value of 6. What you cannot establish here is a condition number 3, where f of x is equal to f of a. Here f of x is equal to 6, here f of a is equal to 2. They're not the same, therefore you don't meet condition 3. If you could literally translate this dot right into this open space and close it up such that this dot ended up right here, then in that instance f of x would equal 6, f of a would equal 6, condition 3 would be met. But that is not the case with this specific diagram. Generally, to have met condition 3, you will have met also the conditions number 1 and 2. Generally, here we don't meet condition 3, but we do meet condition 1 and 2. You have to keep all of these aspects in mind, that for continuity of a function, you're looking at more than just differentiability. You're looking at 3 conditions. Condition 1, f of a must be defined, that value exists, it's within the domain, it doesn't zero out the denominator in any way, that you get an undefined situation, and it is not outside the function. Condition number 2, right hand and left hand limits are equal to each other, they're legitimate output values for that function. Condition number 3, f of x literally must equal f of a literally, and once you meet all of these 3 conditions, you've established continuity of a function. The function has a smooth, gradual change, it lacks abruptness, and it lacks interruption within that course of its interval. Here, you could be looking at an interval from, let's just say, minus whatever value, minus x to here, positive x. Within this interval, here you don't establish continuity literally in this graph, because we showed you that f of x is not equal to f of a, though the first 2 conditions did satisfy. Anyhow, that's continuity in a nutshell. I hope you understand. If there are any situations or questions which arise from here, let me know in comments. Thank you for watching. Have a nice day.